We just see. So for instance, you can write Vk as AK root minus K eta J nu S minus K eta. I will explain what nu S is plus Bk root minus K J minus nu S minus K eta. These are the and you use the asymptotic forms of the Bessel functions to determine A and B, AK and Bk, and they happen to be the following. Okay, all right. Just let me. Okay, you find that Bk is root pi by K e power I pi nu S e power I pi by 4 divided by 2I sine pi nu S, right? And then what do you have? Bk, or you can write, where is the tester? AK as minus Bk e power minus I pi nu S. I need to write what is nu S. Nu S happens to be, okay, just give me a minute. Right, is 3 by 2 plus epsilon 1 plus epsilon 2 by 2. There is a famous solution in de Sitter limit when epsilon 1 equal to epsilon 2 equal to 0, okay, nu S happens to be 3 by 2, okay. You can write this linear combination in terms of Henkel functions as well, but the asymptotic forms of the Bessel functions are, you know, listed. You can be found more easily, and it's better to write in terms of the Bessel functions. Now, what you need to do is that you need to substitute the power spectrum, right? Remember the power, we had the expression in terms the power spectra. Maybe I'll write this here. The power spectrum was what? PS of K was the following. You had KQ by 2 pi squared mod Vk by Z squared, and tensor power spectrum PT of K, if I recall correct, it is 4 into KQ by 2 pi squared into UK squared by A squared, and UK at early times, remember, okay, this Vk with these AK, what do you expect? This Vk will go to 1 over root 2k e power minus ik eta, which corresponds to the Bunch-Davies initial condition. Okay, you can do the same exercise for UK, and for want of space, I will write it here. Remember, UK at early times is supposed to be root 2 by MPL. Okay, for reasons I already explained, root 2k e power minus ik eta. Okay, so you can do the same exercise. I would urge you to repeat the same exercise for the case of tensors, and what you obtain, you know, in a very polished fashion, the power spectrum at late times is as follows. Let me write that down for you. So you obtain the power spectrum to be, right, let me see where I have. Okay, so PS of K to be h squared by 8 pi squared MPL squared epsilon 1. And then you will have some constants, epsilon 1 times C plus 1 minus epsilon 2C. I will explain what is C in a minute. Epsilon 1 plus epsilon 2 log of minus K eta. This is an exact expression, okay, where C is gamma E. This is the Euler constant minus 2 plus log 2. And then in the same way, what you can obtain after some algebra is 2h squared by pi square MPL square, okay, 1 minus 2 epsilon 1 C plus 1 minus 2 epsilon 1 log of minus K eta. This is arrived at minus K eta tending to 0 limit. These are arrived at. And the formal definitions of NS and NT are as follows. formal definition is ns minus 1 is d log ps of k by d log k, all right? And you can read it off. This happens to be minus 2 epsilon 1 minus epsilon 2. I hope that is correct, okay? And NP is d log pt of k by d log k, which is minus 2 epsilon 1, all right? And the point to note is the following. You have an R is something like PT by PS, okay? And if you ignore all this, all these constants, if you take a ratio of this, okay, you can convince yourself this 16 epsilon 1. And this is often referred to as a, okay. So this is written as minus NT, minus 8 NT. And this is often referred to as the consistency relation. The slow roll consistency relation that relates tensors and NT. Imagine you have a scenario where you are able to actually measure R and you are able to measure NT, and you can examine if you have inflation, slow roll inflation driven by a single scalar field, you expect such a relation between the amplitude of the tensors and the index associated with the tensor. Just a couple of other remarks, okay, before I talk about constraints. So what do you have? You have, if you plot PS of K, right, and PT of K, they are nearly scale invariant, okay? Okay, look, the index NS minus 1, as we shall see, is like 0.96, okay? So NS is 0.9, that is correct. No. No, NS is 0.96, sorry, okay? NS is 0.96. So NS minus 1 is 0.96 minus 1, which is like 0.04. So what happens is that, you say the spectrum has a red tilt. In other words, it has more power at large wavelengths or small k, right? And it has a, lower power at large k or small wavelengths. And therefore, you say it has a red tilt. It's like that. It's not like that. That's a blue tilt. And it's nearly scale invariant for reasons I mentioned. And this is the observational constraint. I will just comment about it further when I talk about constraints on models of inflation. And so PT is somewhere here with a slightly different index, okay, depending on the model. And again, what you should recognize is that NT is negative. It has a red tilt. So if you have a blue tilt, right, you have a problem with inflation. You see tensors and you have a blue tilt. Well, it's probably not generated during inflation, or you need to invoke other mechanisms during inflation or post-inflation to change the tilt. Okay, all right. And what are the other remarks I wanted to make? So I want to make sure that you recognize this. This is a more formal way of arriving at the result. Okay, that was to illustrate that you can obtain the spectra very roughly, the essential aspects of the spectra very roughly using those tricks, okay, by matching the sub-Hubble and the super-Hubble modes. And more formally, you need to write down the solution in terms of the Bessel or the Hankel functions, take the sub-Hubble limit to impose the Bunch-Davies initial conditions. Having imposed, you will get those conditions for AK and BK. I wrote it for the case of scalars. You can do the same exercise for tensors. And then you take the super-Hubble limit. You can write it nicely in this fashion. I will include some references. Some of the references already listed may write power spectra in this form, okay? And I will include further references towards the end of all the lectures. NS and NT are more formally defined in this fashion, okay? And you can read it off because the derivative is going to appear from here, and this is NS minus 1, and this is rather, NT, okay? So now what we need to do is that we even in the last class, we related epsilon 1 and epsilon 2 to epsilon v and eta v. Epsilon v was a derivative, essentially v phi by v, modulo factors of MPL squared by 2, and eta B involved V phi by V, the second derivative. So now what we would like to know is that, if there are constraints on NS and R, what cosmologists do is as follows. Okay, now let's move on to, I have completed my discussion about formal way of deriving at the spectra and slow roll inflation, and these are the exact spectra. I would urge you to derive them using asymptotic forms of Bessel functions. Now, what essentially happens is as follows. As I had indicated in my overview lecture, okay, so you assume PS of K to be some AS K by K star power NS minus 1. K star is often referred to as the pivot scale, okay? And what one assumes is that one assumes R is nearly a constant, okay? In fact, the value of R is quoted at some scale where they know very well, okay? And so essentially, there are two parameters, as I mentioned at that initial talk. AS, we know very well, okay? It's often referred to as Kobe normalization, Kobe or CMB normalization. And we know its amplitude very well, normalization. And that happens to be 2 times something like 10 power minus 9, 2.3 or something like that into 10 power minus 9. And what we are trying to arrive at is constraints on R and NS. We haven't seen the tensors, so we are still not worried about NT, okay? And you would have recalled, if you recall, I had constraints of this type. So you had NS, where you had something like 0.96 here, and let us say this was 0.05 or something, and the best constraint, okay, was something of that type, okay? And the strongest constraint, it's like the R, the 1 sigma is like 0.036 or something. I hope, this is the constraint you arrive at. So these are constraints arrived at CMB data. So the question is, where does, your model, inflationary model, lie in this plane? Okay, so what do we have? You have NS is equal to, can you tell me, it was 2 epsilon V plus 6 eta V, is it? Let me pull out my notes. Both are 2, is it? Okay. One was 6 and other was 2, plus 2 eta V. Okay. And then R was 16 epsilon 1. Okay. So one of the exercises you needed to do was, I have erased the index. It was what? Minus 2 epsilon 1. What was the index in terms of epsilon 1 and epsilon 2? Okay. You need to relate that to epsilon V and eta V. Okay. Eta V is a combination of epsilon 1 and epsilon 2. Using the slow roll approximation, I would urge you to establish that. We want to write everything in terms of the scale, in terms of the scalar field. Okay. So this is epsilon B. Okay. So let's consider some examples, right? So just give me a minute. Right. Okay. So what is our goal? What are the things we know, and what are the things we don't know? Okay. What we don't know is when the mode left the Hubble radius. Okay. Let us say these are evaluated at some pivot scale. Pivot scale is chosen to be sometimes something like 0.05 megaparsecond. Okay. This is very close to this thing called KEQ that we arrived at. Recall what was KEQ? That was the scale that re-entered the Hubble radius at the time of equality, right? It's very close to that. We know the CMB amplitude very well on those scales. So what we don't know is when did this mode leave the Hubble radius? That depends on the energy scale of inflation, etc., etc. Okay, so there is some uncertainty. Okay, we will assume that this scale, okay, the scale at which we have constraints on R and NS are left at 50 or 60 E-folds prior to the end of inflation. Remember, I have been constantly saying you should remember this picture. Let me draw this, so this is the CMB constraints on R. CMB and possibly other cosmological data as well. Okay, remember this plot that I have. You have, lambda log of lambda p and dh, the Hubble radius, and they leave the Hubble radius at some time. This is inflation, and this is radiation domination, and what has been plotted against logarithm of a number of E-folds. And I have been saying that the number of E-folds at a time when the mode leaves the Hubble radius is counted from the end of inflation. This is often referred to as n subscript k. We will need that repeatedly as we proceed. Okay, so let's consider first power law inflation. Okay, I've already indicated power law inflation as a problem that there is no end of inflation, but nevertheless, let us see what happens. Okay, in power law inflation, if you recall, V phi was of the following form: m power 4. Well, I didn't derive all the terms, but I had indicated that it was exponential. Some phi I by MPL. But if you recall, the first slow roll parameter was a constant, and therefore the second slow roll and higher order slow roll parameters were all 0. Okay, and it's not surprising, it is exponential. So epsilon V is essentially 1 over Q, correct? Is 1 over Q. And eta VV is also 2 over Q. Okay, that's what you have. And therefore, what do you have? R is 16 epsilon V, which is 16 by Q. Okay, and NS is what? If you substitute that here, what do you obtain? You get 1 minus 6 by Q plus 4 by Q, okay, which is 1 minus 2 by Q. Now, inflation doesn't end at all here. So there is nothing equivalent to NK here. Okay, it's all a function of Q. So if you choose Q to be 50, for instance, right? Okay, what will you get? If you choose Q to be 50, because I know NS very well. If I choose this to be 50, what will I obtain? Okay, this is NS is 1 minus 2 by 50. What is that? Okay, this will be like 0.96. Is that correct? Okay, NS is like 0.96. This is 1 over 2 over 50. This is 1 over 25, right? Okay, yeah, it's like 0.04, 0.96. So what you want is that if you have power law inflation and you want to lead to an NX, that is, if you want an adequate tilt, red tilt in the power spectrum as suggested by the observations, what do you need? You need Q to be of the order of 50. But what happens to R? R is 16 by 50. This is like 0.3. Okay, it's somewhere here. All right, depending on the scale at which you plot, it's much larger than the constraint that we have arrived at. So, despite the problems that there is no exit to inflation, if I just naively thought, asked whether power law inflation is valid, it leads to a very large tensor to scalar ratio. So this is power law inflation. We will turn to large field models now. Oh, okay. I hope you have that picture in mind. Okay, these two pictures you've got to have in mind. The constraints on, you need something which is close to NS. Okay, there are strong constraints on NS. Even 0.95 or something like that is, I think, at least 2 to 3 sigma away. Okay, from 0.96. So you need something very close to 0.96. We know the tilt of the spectra on large scales fairly well. Okay, so large field models. Large field models. So what is this? We are thinking of we are thinking of potentials of the following form. Some m power 4 phi by mp power, or v naught mp by phi by mpl power n. We had seen these cases earlier. Okay. So what do we need to do? We need to calculate. We know how to obtain the solutions. Okay. So remember, we had seen that 3h phi dot, I'm repeating what I had done earlier, is V phi, okay? And remember, phi dot is h phi n. Do you understand the notation? Phi subscript n is d phi by dn, so it is h phi n. So this is 3h squared if I strike the dot n, and then I have 3h squared mpl squared is roughly v, okay? I can take the ratio of this, 3h squared goes away, okay? So what am I left with? I'm left with n equal to integral d phi, there is a minus I have missed out, minus, okay? And then what do I have? V phi by V, correct? Which implies this is, okay, essentially, this is n by phi. Is this correct? No, phi by n, sorry, the other way around. Is that correct? Have I made a mistake here? No, this cannot be. This has to be V by V phi. Sorry. I'm mixing these, okay? So, okay, let me write it in one more step. D phi by dn, correct, is equal to, right? D phi by dn equal to mpl squared minus V phi by V, okay? Or dn, n equal to minus 1 over mpl squared integral d phi v by v phi. Okay, this is what you need to remember. And what we are going to integrate is that we are going to integrate that. So let me understand my notation. We are going to integrate from phi to phi end, right? And we know where phi end is located. Phi end is located when epsilon v is 1. Okay, so what do I have? So remember these expressions. I need. So what do I have now? So I can write n as essentially, in this case, this is v by v phi is phi by n. So upon integration, I will get n equal to minus 1 over 2 mpl square, right? Times n phi n square, sorry, phi square n minus phi n square. Okay, right? And epsilon v equal to 1 implies, we had shown this earlier, if I recall correct, n by root 2 mpl. If not, it's straightforward to show. So what do you have? You can write phi square n as mpl square into n squared by 2 plus 2n n. Okay, all right? And, okay. Now you can ask, you're counting n from the end of inflation. Okay, so now that number, if it's of order 60 or 50, that will determine you the value of phi. So you know the value of phi when the pivot scale exited the Hubble radius. Why are we interested in? We are interested over those domain. I know ns very well and r very well. So I just need to calculate those quantities, okay? So what do you have? For n equal to 2, okay, all right? So you can, okay, let me consider n equal to 4 first, okay? And for n equal to 60, capital N equal to 60, what do you obtain? You obtain phi 60 to be something like 22 mpl. All right, okay? For n equal to 2, okay, and n equal to 60, you get something like phi at 60 to be like 16 mpl. Okay, now you need to calculate, all right? You need to calculate what is the value of epsilon v and eta v at these cases. Okay, where is that listed here? Just give me a minute. Okay, I have just, right, just give me a minute. Right. Okay, so, right. For n equal to 4, so let me write it in this fashion. Okay, n equal to 4, n equal to 60, this is what it is. And you obtain R to be 0.26, NS to be about 0.95. Okay, for n equal to 4, when n equal to 60, I will let you calculate what is phi, etc. And you obtain R to be 0.31, okay, and NS to be 0.94. Okay, you can see, they are being ruled out at a sigma, 2 sigma, and more importantly, the constraints are R. Okay, so in other words, if I have a lambda phi 4 model, which is a renormalizable potential, well motivated, okay, it's not consistent, it cannot act as an inflaton. That's the bottom line. Okay, now if you consider n equal to 2, all right, if you consider n equal to 2, and then n equal to 60, okay, I will let you calculate. R happens to be about 0.13 and NS is 0.97, okay, and n equal to 50, okay, R happens to be 0.16 and NS is 0.96. This fits the data very well, okay, but R is large. So an m squared phi squared model, m squared half m squared phi squared model is also ruled out by the data. Okay, but what is interesting is the following. If you consider n equal to 2 by 3, okay, it's an index less than 1, okay, and what you find is that n equal to 60, if you have n equal to 60, you have R is 0.044 and NS is 0.98. Okay, and n equal to 50, R is 0.053, okay, and NS is 0.97. So in other words, 5 power n, n less than 1 models do better. In other words, okay, that's something you need to keep in mind. So these are large field models. What it essentially implies is that large field models are not largely consistent with the CMB constraints. What happens to small field models, it involves a bit of lengthier exercise, okay, in terms of calculating these. I'm going to leave all of that for you. I have already indicated with the example of a large field model how you can obtain phi of n in the slow roll approximation. So what do? You determine where inflation ends, see where the field will be. Now you have a small field models. So the large field models behave like that. Large field models, small field model behave like that. These are the small field models. So inflation occurs in the large field models here. In the small field models, inflation occurs here. V of phi, right, as a function of phi. And the small field models I have considered are as follows. V small field models, right? And we are considering potentials of the following form, something like 1 minus phi by mu power q. Okay, and we assume mu to be less than MPL. Okay, mu you assume to be a few MPL and so on. And I'm just going to indicate what happens for Q equal to 2. Okay, for Q equal to 2, after some exercise, what you find is that n equal to 60, R is equal to 0.028. All right, and NS happens to be 0.964. Okay, so these models do much better, as you can see. Okay, so small field models are consistent with the cosmological data. The model that's as of today's data is an ideal model is the Starobinsky model, which I have already mentioned. So V of phi is V naught, right? 1 minus exponential, let me get this right, okay, minus root 2 by 3 phi by MPL whole square. Okay. And again, you can solve them in the slow roll approximation, solve for phi in the slow roll approximation. And what you find is as follows. For, you can show the following. Let me just get me in. You can show that NS is like this, is minus 1 minus 8 into 4n plus 9 divided by 4n plus 3 whole square. Okay. And let me see whether I have R expression for R. Just give me a minute. R happens to be 192 by 4n plus 3 whole square. Okay. And for large n, what do you have? NS is like 1 minus 8, 32n divided by 4 squared n squared, right? Is that correct? 1 minus 2 by n, right? Okay, something like this. So, and similarly, R is what? Is 192 by 16n squared. Okay, I will let you do the division. So what you find is that for n equal to 60, R is 0.0033 and NS is 0.97, and for n equal to 50, okay, you find that R is 0.0047, right? And NS is 0.96. Okay, this is the Starobinsky model. Okay, so I would strongly urge you to fill in the algebra and derive these results. So the bottom line is that, the Starobinsky model is remarkably consistent with the data. The other day, there was a question about, what if tensor to scalar ratio is seen or not seen, and there are stronger and stronger constraints, other theoretical models which can be consistent with the data. NS has been measured, okay? So NS is not going to change unless there's some drastic change somewhere. NS is not going to change, okay? I mean, R remains the holy grail, okay? And what will you do if you want smaller and smaller R and with no change in NS, okay? And there is a very popular model which can do that for you. Let me write that model down, just bear with me. These are called the alpha attractor model. I'm just trying to get all the constants correctly. And there it is. Okay, these are called alpha attractor models. They have different names as well, okay? And there are other forms of the potentials that are possible which will do a similar job. This is, some V phi equal to some V naught. It's like very much like the Starobinsky model with just some 2 parameters changed, minus 2 by 3 alpha. Notice there is an alpha that has been introduced, MPL, whole power some P, okay? P equal to 2 corresponds to the Starobinsky model, and alpha equal to 1. These are correspond to the Starobinsky model. And you can do the same exercise after some lengthy algebra. What you obtain is as follows. Let me get the values of R and NS. Okay, for large NK, right? This is what I've been calling as NK. What does N subscript K mean? It's the number of E-folds before the end of inflation, the scale of your interest left the Hubble radius. NS happens to be 1 minus 2 by NK. All right. And R is 12 alpha by NK. 12 alpha by NK squared. Okay, that's the point. Is this 12? This is 12, right? This is 12. All that happens is that the alpha sits there. And P, it seems completely insensitive to P. Okay, so essentially what happens is that the Sriramkumar model does a good job today. It gives you N of close to 0.96 and an R, okay, which is consistent with the data. Okay, if the constraints on R, grow stronger and stronger, and you have smaller and smaller values, what do I need? I just need to keep reducing the value of alpha, okay, and I can lower the value of R, okay, but NS will remain where it is roughly. Okay, so these are this is the manner in which you arrive at roughly constraints on inflationary model, okay, from the CMB data. Well, this is a loose way of arriving at constraints. If you want to be precise, what you need to do is that you calculate numerically the power spectrum in an inflationary models. There are parameters. For instance, if you have the large field model, there was just one parameter that was present. Well, there are two parameters. You have to fix N, okay? Remember, V naught 5 power N. You fix the value of N. And you may ask, what fixes the value of V naught? I didn't talk about what is V naught. V naught is essentially fixed by the scalar amplitude, okay? By the scalar amplitude. And for instance, if you have an M squared phi squared model, okay, if you want a scalar amplitude of about 2.3 into 10 power minus 9, you will find that M, small m by MPL, is the order of about 10 power minus 5 or so. Okay, all right. Similarly, in such a model, all right, V naught will fix the overall amplitude. Okay, and you have to understand that in such cases, everything is fixed for you. Okay, once you give you a value of the parameter, it determines the value of the scalar amplitude, the scalar spectral index, the tensor spectral index, the tensor amplitude, everything. Okay, so what you need to do is that you need to compare each model with the data. Okay, and you will have values of the parameters. Okay, like V naught and alpha and P, which will lead to best fit to the data. And you have to see whether it compares better with a simple, I can write the power spectra in the fashion I had written in terms of AS, NS, AT, and NT. And you can compare with the simple power law forms of the power spectra. How does it compare these low roll inflationary models? What one finds is that, models such as the Sriramkumar model, okay, will lead to fits which are comparable to that simple scenario, okay? While, as you can imagine, the M squared, phi squared, lambda, phi 4 model, etc., will not lead to an equally good fit to the data. They will lead to a poor fit to the data. And since, the data does not discriminate between different values of R, models which lead to different values of R, for instance, it will not be able to constrain the value of alpha, okay, the CMB data. All these values below a certain threshold, alpha being 1, okay, will be any value of alpha less than 1 will be consistent with the data, and so on. Okay, so with that, we come to conclusion of constraining, slow roll inflationary models with the, constraining slow roll inflationary model with the help of the cosmological data. Now we move on to non-trivial scenarios. I will explain the motivation for considering non-trivial scenarios. What do I mean by non-trivial scenarios? Non-trivial scenarios correspond to situations where the field is not rolling slowly. Okay, I've been talking about potentials. I've drawn potentials of small field models, large field models, Sriramkumar model, and they all are smoothly evolving, right? And therefore, you can expect them to lead to slow roll inflation. That's just because it is smooth doesn't necessarily mean it will lead to slow roll inflation. If you have a point of inflection, for instance, it's known that it leads to non-trivial dynamics. I will talk about some part of it over the next lecture or so. So what we are going to study is deviations from slow roll inflation. But deviations from slow roll inflation can be of many types, okay? And what essentially happens is that people have been focusing on deviations occurring either during the early stages of inflation, okay, or during the late stages of inflation. And there are different motivations to consider these features. And of course, as I mentioned, deviations can be of many, many types. There are many varieties of deviation, and each of them will lead to specific features in the primordial spectrum. So what I'm going to do is discuss features arising in two scenarios. One, I will introduce a feature in a potential, which will lead to a feature in my power spectrum. And another, I will consider a scenario of what is known as ultra slow roll inflation. I talked about it very briefly in my overview lecture. I'll consider these scenarios and I will discuss the form of the power spectra that will arise in these two cases. Okay. These are just simple examples which are analytically tractable. In some situations, the deviation from slow roll will be such that you will not be able to analytically solve the equations. You have to turn to numerics. Generically, you have to turn to numerics to integrate the background and the perturbations in models that lead to strong deviations from slow roll. Maybe this is a good time for me to answer one or two questions before I move on to generation of features. Questions? Yes. So I remember I said something called the decomposition theorem. I didn't prove it, but you can look at some of the texts for a proof, okay? They evolve independently.
Yes, sir. So I have to go through the algebra, but can you just indicate that why from the scalar V phi I can get an information about the tensor to scalar ratio? Because the scalar and tensor fields are completely independent and there is whatsoever no coupling between them.
Look, please understand the tensor to scalar ratio is something I have conveniently defined to describe in terms of one parameter. Cosmologists, when they compare with the data, want to deal with small number of parameters. And then you can go sophisticated and compare model by model with the data. Okay. So it is all okay. Tensor to scalar ratio is just, look, it's just a way of saying I know the tensor amplitude, nothing more. Because I know the scalar amplitude very well. Okay. And I had shown, if you look at I erased the tensor spectrum, power spectrum, right? It is h by, if you look at it, it has to be dimensionless. It happens to be h by MPL squared. The scalar power spectrum is h by MPL squared epsilon 1 in the denominator. So epsilon 1 is model dependent. Right? You can see, you will see in some cases, epsilon, look, it is 16 epsilon 1, okay? In fact, this is the Sriramkumar model. What happens is that it is the epsilon 2 which contributes here. Epsilon 1 is rather small in S, okay? And it is the small value of epsilon 1 that leads to small value of tensor to scalar ratio. And that's why it's consistent with the data. In some sense, data is pointing to scenarios where epsilon 1 is small and epsilon 2 is large. Okay? I haven't completed my argument. So coming back to h by the tensor amplitude, it depends on h by MPL. So I know the scale of inflation if I know the tensors. Okay? Just by knowing the scalar amplitude, what it means is that I know what is the value of, for instance, V naught immediately. For now, I'm fixing, okay, I'm fixing it by the scalar amplitude, but I will know stronger constraints. For instance, if I take the Sriramkumar model, well, there is no other feature here. So there is a tensor to scalar ratio. If the tensor to scalar ratio happens to be smaller than this or larger than this, the Sriramkumar model is ruled out. Okay. I know the scale of inflation if I can see tensors, because I know h by MPL, and in the slow roll approximation, h squared is like V. Did I answer your question?
Yeah.
Okay, all right. Maybe one more question before I proceed. Okay, if there are no questions, let's move on to study generation of features. Okay, there was a question? Yeah.
Do you see shift beyond Hubble radius in the power spectrum? Is it measured?
So you have to be, this is not shift as, as it occurs in a Doppler effect. This is not, I didn't use the word red shift. Oh, you're talking about galaxies and observations and so on. Is that what you're referring
Yes.
to? Okay, firstly, this is the power spectrum of perturbations generated during inflation in the early universe. This has got nothing to do with the power spectrum of light emitted by a galaxy. Okay, so this is very different. So I haven't talked about red shift. I've been talking about red tilt, okay, and blue tilt. Whether the power spec, okay, there are perturbations in the early universe, whether they have more power on large scales or small scales. What we have argued is that if it is generated during inflation, okay, slow roll inflation, you need to see a red tilt in both the scalar and tensor power spectrum. Yeah. Are there any other questions? Okay, let's move on to discussion of generation of features. It's simple. If you want features in your primordial spectrum, okay, you want features in your inflationary potential, as simple as that, okay? Otherwise, you are largely left with slow roll inflation, and that will lead to featureless, nearly scale invariant power spectrum. Now, why do you want features? I had mentioned as to, I will explain why you want features in the primordial spectrum. So what do you have? We talked about PS of K. We'll not worry about tensors, we'll focus on scalars, all right? And we said in slow roll inflation, I have a spectra which is like that, okay? And what we are focusing on, we'll be largely focusing on scales initially, or these scales, okay? 10 power minus 5 to 1 megaparsec inverse. Why? Remember, these are what? Our cosmological scales and are constrained by the CMB and the large scale structure. Now, let us say, let us take a scale, okay? Now, we would like to ask, what is the scale that leaves the Hubble radius at the end of inflation? Okay, let's estimate that. We assume slow roll inflation. In fact, for simplicity, we'll assume d zeta inflation. Okay, so what do you have? You have K star, right? Okay, let me draw this picture maybe again, right? So this is logarithm of lambda p or dh, plotted against logarithm of A, which is number of e-folds. Oops. And then something like that. And modes leave the Hubble radius, okay? So this is Hubble exit, okay? Let's say K star is A star, H star. K equal to H is Hubble radius. I put stars to indicate some pivot scale leaves the Hubble radius at that time. I'm going to assume for simplicity, H is almost a constant. H is just H, it's a constant. Okay, maybe I should use something like HI to indicate that it's a constant Hubble scale during inflation. So now, what do we have? K star leaves the Hubble radius 50 e-folds before the end of inflation. We were just discussing that, okay? Now, what are the uncertainties? Why are we changing 50 and 60 will become clear once I discuss reheating. At least it will become partly clear, okay? This is because we don't know what scale at which inflation took place, what happened post-inflation, etc., etc. Now, what do we have? A end is what? Is equal to A star e power n star, right? Okay, so A star is, okay, I'll come to that in a minute. I will also call something called KE which is AENHI. What is KE? KE is the scale, this scale here. It's, I should draw it correctly, like that. This is KE. This is my K star. And this duration is 50 eFols, which I've called as NK or N star. Okay, maybe I should use that notation. NK. No, that's fine. A star, N star, NK. Yeah, or N star. People use it interchangeably. NK, which is equal to N star. Is that okay? All right. What is KE? Is the last mode to leave the Hubble radius. Inflation imprints its effects on perturbations over this entire range of scales. Okay. From the larger scale, which we have stretched from 10 power minus 4 to 10 power minus 5. Okay. Two, we are trying to determine what the scale is. So what will this be? Okay. So I can take a ratio of this, right? Okay. So HI goes away. So K star by KE is what? Help me. A star by A end, which is E power N star. No, there is something wrong here. Okay. A star E power minus N star. Our KE is E power N star K star. Okay. If N star is 60, I know that E power 26, I'm sorry, E power 60 is like 10 power 26. Okay. So something like, K star is 10 power minus 2, 10 power 26. That's a little too much. So E power 50 is like probably 10 power 23, 24, something like that. So you're talking about something like 10 power 19, 10 power 20 megaparsec inverse. Okay. So if you calculate power spectra and slow roll inflation, you will get I have enlarged this tilt, but I haven't plotted anything on this axis, so I presume it's fine. Okay, you will get spectra like that. Okay, it'll be like that with with nearly scale invariant amplitude until modes very close to the end of inflation. Okay, so this is probed by CMB. This is probed by CMB scales. Okay. Large scale structure probes over a small range of scales. Okay, this is large scale structure somewhere over this domain. Over this domain, you have what is known as spectral distortion. You should ask Shiv Sethi to speak about spectral distortions. Okay, and then here we don't have any constraints on these scales, weakly constrained or weakly or poorly constrained. Okay. So what people have been interested, including some of us, okay, Tarun Sauradeep, for instance, okay, are if there are some features here, okay, Yashi here has been studying as well, or if you have a drop in power, okay, or if you have some burst of oscillations over some intermediate scale, these all lying in the CMB scales, okay. Raga also has recently studied, if there is a dip in the power spectrum, can it, large scale structured data can point to, can support such a dip. We will talk about why a dip should arise as we proceed. Okay. So there are various features that have been considered over the CMB scales. You can compare with the data, okay, and ask whether some of those features fit the data better than the nearly scale invariant spectrum I drew originally. Okay, and indeed, some sets of spectra improve the fit to the data significantly. And if you want to generate those features, you need to have deviations from slow roll. I'm not going to focus on spectra that lead to improved fit to the data. I'm just going to illustrate with the help of a simple example how deviations from slow roll are generated and what type of features they generate. Okay, so this is on large scales. Okay, so remember I mentioned this is of the order of 10 power minus 9. Okay, all right. I haven't, there has been interest, as I mentioned in the original talk, if you recall. Okay, so if you draw on very large scales, okay, CMB scales are here. All right, this is 10 power minus 5, 1. Okay, and this is like 10 power 20, all in units of megaparsec inverse. And let us say this is 10 power minus 5. Can we have power spectra which is like of order 1 or 10 power minus 1? and what are its implications. Okay. What we will see, what we will discuss, time permitting. Okay. I will discuss, but whether I will be able to do justice to the, to provide a complete discussion, I do not know because of time constraint. Okay. What we will see is that if you want larger number of primordial black holes to be produced in the early universe, slow roll inflation with amplitude of about 10⁻⁹ will not produce adequate number of good number of primordial black holes. I talked about this constraints on something called FPBH. Will be very small. So if you want to produce larger number of primordial black holes, the initial interest arose to examine whether some of the LIGO black holes discovered by LIGO through detection of the gravitational waves emerging from merging black holes could have been primordial because they had this strange distribution of masses, and that investigation continues. Okay, and so if you want to produce enormous number of black holes, you cannot have such a scale invariant spectrum at CMB amplitudes. You need excess power on small scales. You have to enhance the power on small scales in order to produce features, strong features in your primordial spectrum, which lead to larger number of primordial black holes. And so the features we shall be, the reason for considering features, as I said, I've given two indications. Okay, one, to examine whether there are deviations from slow roll can improve the fit to the data, or in other words, whether inflation is truly of the slow roll type, or there are deviations from slow roll, or in other words, only certain specific types of models are more consistent with the data than smooth models. And on smaller scales, remember the CMB stops constraining your primordial spectrum at scales of order of 1 megaparsec or so, 1 megaparsec inverse or so. On much smaller scales, one is interested in generating features, for instance, to enhance production of primordial black holes. And what is interesting is that Abhi was asking a few minutes back, as to that the scalars and tensors, evolve separately. And they do evolve separately, okay, if you restrict yourself at the leading order in perturbation theory. But you go beyond the first order, what one can show is that second order tensor perturbations can be produced by scalar perturbations. And these are what are known as scalar induced gravitational waves. And so if the scalar perturbations amplitude are significantly large, they can generate tensor perturbations at the second order. And those amplitudes can be large enough, as I indicated in my initial talk, to be comparable to the sensitivities of the current and ongoing and forthcoming gravitational wavelets. So these are the motivation for examining features. As I said, we will study features generated in two different ways. One from a feature and a potential, and another where we model the background evolution and try to arrive at spectra that have been considered often in the context of PBH, enhanced PBH formation. The first model we will study is again due to Starobinsky. It's a Starobinsky model, but it's a different Starobinsky model which admits a deviation from slow roll. So what we have is the following. This again, let me call this a second Starobinsky model, Starobinsky model 2, and we have a potential, right? And we have some V naught plus A, no, what should I write? Plus A plus into phi minus phi naught. Is that correct? Let me get my form of the potential correct. Okay. Right, phi minus phi naught and V naught plus A minus phi minus phi naught. Notice A plus and A minus are different, okay? And if it was the same, I would have had a potential which is like this, right? I would have had some V naught, something like this, okay? Now what happens is that, and it would have gone all the way up to V naught, okay? if it was just A plus phi, it would have been like this up at V naught. But what do we have at phi naught, right? I have a different slope at phi equal to phi naught or phi naught. Okay. This is phi, V of phi. Okay. And what we are going to assume is that the V naught is large. Okay. In other words, the background dynamics is largely driven by this V naught. Okay. And as a result, what do we have? There is slow roll. Okay. The field starts somewhere here, right? It's slowly rolling down the potential. Oh, I'm sorry. I forgot to notice the time. I've run over time. I'll just make a few remarks and stop here. We'll continue in the afternoon. I completely lost track of time. Okay. So this is a linear potential, right? And it's going to lead to slow roll inflation. And what we are going to assume is that to allow, solving everything analytically, we are going to assume that V naught is large. Therefore, I'm going to write this as 3 H naught square MPL square is V naught. Okay, is roughly V naught. And the H naught is determined by that. And it is d zeta, right? If it is going to be driven by a constant V naught, we know that the A of eta is going to be like minus 1 over H naught eta. For convenience, I'm going to use H naught to denote the Hubble parameter. Okay. This has got nothing to do with the Hubble constant today. This is the Hubble constant during inflation, and it's driven by this constant potential V naught. And as you can imagine, it's going to slow roll initially, but the moment it hits that change in slow, it will momentarily deviate from slow roll inflation. And what we will see is that we need to solve for that. The slow roll approximation is violated. So we need to go to the exact equation and solve for it. Okay. And what we will see is that, because A eta is given by this one, epsilon 1 is always much, much smaller than 1. That is when the d zeta approximation is valid. Epsilon 1 is much smaller than 1. Remember, the slow roll approximation corresponds to when the hierarchy of slow roll parameters, epsilon 1, epsilon 2, etc., are much, much smaller than 1. Okay. But here, though epsilon 1 is much smaller than 1, we will see epsilon 2 will become large. Okay. And the higher order slow roll parameters will also have the corresponding effects. Okay. And it is this deviation from slow roll, what will happen is that will lead to strong features in your primordial spectrum. And it is clear that it is the difference in A plus and A minus will lead to the jump. Okay. The larger the difference between A plus and A minus, the larger the deviation from slow roll in some sense. And we will see the power spectrum. Okay. What you will see is that, what happens at very early times, there is slow roll. At very late times, there is slow roll. Okay. We are not worried about end of inflation, etc. This is just you can treat it as a pedagogical example. It has its utilities. Okay, where you are able to solve for the power spectrum analytically. So what happens? There is a regime where the modes leave here, and there is a regime where modes leave here. And during this domain, you have near d zeta, right? So what will happen? There will be scale invariant spectrum on one side. There will be scale invariant spectrum on another side, or modes which leave at early times. The modes will leave here at early times during inflation, right? I hope you understand. This picture of inflation that one draws, there is some effect that will happen as the field reaches phi naught, okay? Again, I'm plotting, logarithm of lambda p and dh as a function of n equal to log a, okay? So here, when modes leave here and modes leave here, they just see slow roll, okay? Here they are in the sub-Hubble regime, okay? These modes are well inside the Hubble radius when this happens, right? At this time, they're here, okay? These, when this happens, they are well outside the Hubble radius. And the Hubble radius, we know, they freeze, okay? Not quite, there can be small effects because of deviation from slow roll, but a good approximation, they freeze, okay? When they're well inside the Hubble radius, these changes are not going to be affected, okay? So you will get a scale invariant spectrum on both sides, but this deviation from slow roll will affect the manner in which these scale invariant regimes, they will not be at the same height, okay? So this will lead to a power spectra, which will, as we shall see, of the following form. There'll be scale invariant, there will be scale invariant, and there'll be something like this, okay? As you can see, there will be ringing, and which will eventually die down and that will be the form of the power spectrum Ps of K. Okay, as a function of K. These corresponds to modes which are leaving at early times. These are the modes which leave at late times, and they are affected by what happens here. Okay, and in between, you need to carry out a careful analysis in order to arrive at the form of the power spectrum. So we will discuss the Starobinsky model, and we will discuss something known as ultra-slow roll inflation, which will lead to a specific power spectra with a peak. Okay, we'll discuss these two models. Again, I will not be able to discuss everything, all the details. Okay, I will leave some steps for you to fill in, and I will indicate. I've already indicated the form of the spectrum here. I'll just provide justification for that and move on to discuss ultra-slow roll.
So we will just take 2 online questions.
Sure.
Offline questions we can come to later. So there is a question about vector perturbation. This is, they have asked, could he explain vector perturbation after the lecture? I will forward the question to you and you can take
Sure,
it at
sure.
a later time.
I haven't had time to write down the equations for vector perturbations. I will write that and make some remarks. Okay.
Okay.
But they are welcome to speak to me offline as well.
Okay. And there was another question about perturbations in warm inflation. I believe we can touch upon it later at some stage.
So I'm not qualified. I should confess I don't completely understand the perturbations in warm inflation. So I am not sure whether I'll be able to confidently answer questions in that regard.
Okay, that's all we have.
Thank you.